Hello, welcome to another episode of Mystery Science. Today we're going to be looking at energy, work and power. Remember, if you want to follow along with the textbook, there will be links below to an Amazon affiliate link where you can pick up a copy of the textbook itself. Right, so let's dive straight on in by looking at energy. Let's have a look at gravitational potential energy. What is it? So the gravitational potential energy is the energy that an object has by virtue of its position in a gravitational field. What does that mean? It means that if you have a body and it is above a surface where the surface has a gravitational field, the body will be attracted by the force of gravity. Now, the potential for this to fall is its potential energy. By the time I release this, all of the energy that could possibly be converted into kinetic energy by the time it hits the floor, that is the potential of this object. So the gravitational potential energy is given as mass multiplied by the gravitational field strength multiplied by the height above the surface. Remember, this is weird. If I have a surface and the object is likely to land on the surface, then its gravitational potential energy is much less than when I take away my arm. Now that's quite a weird one to think about because I haven't actually given the object any more energy, but it has more gravitational potential energy. It can't fall as far here because I'm going to catch it because I am a superstar goalie, but if I remove my hand and take it away, it's now going to fall all the way to the floor. So that's gravitational potential energy. It's a product of the height above the floor, or where it can possibly land. Remember that actually it's trying to pull this object. The Earth is trying to pull this object towards the center of mass, which is the center of the planet. Give or take a little bit of roughness and weird bobbliness that this planet has, remember it's not a perfect sphere. Now, the other thing you have to consider is that this really is for the surface of the planet, and I think we'll go through this in a bit more detail, but MGH doesn't actually work the further away you go because gravity works by an inverse square law. When we start to look at solar physics and space physics, we're going to see that actually gravity, whilst it's an infinite force and its effects can be felt across the universe, it actually gets smaller by an inverse square law, much like the beams of light. So the gravitational field strength, for example, of the Earth, which is given as 9.81, isn't 9.81 a few miles above the Earth's surface. So all of these problems where you're going to be asked to solve these will be around the Earth's surface. Okay. So we shortened this to capital E with a small p as a subscript. That gives you potential energy is mgh. Now we usually say that the energy is mg multiplied by the change in height. We're going to be looking at the change in potential energy most of the time. So as I've said, it's at the surface of the Earth where this is applicable. So let's have a look then at a block of mass 500 kilograms, and it's going to be lifted 0.75 meters off the floor. How much gravitational potential energy is gained? Obviously, as usual, pause this, have a go at this, do the working, and then I'm going to go through it in a second. And if you're one of my year 12s, then you better be doing that and then submitting it to me on Show My Homework. So here we go. Here is a Lego man. This image is on Creative Commons license, so it's okay. If not, please don't sue me, Lego company. And this construction worker is going to pull the rope and he's going to lift this mass of 500 kilograms. Currently it's on the ground, so its height is 0. So it's going to lift the block. Here it goes. Brilliant. Now its height is 0.75 meters. So what has happened? We have a look at our equation. E equals mg delta h. The change in height is 0.75 meters. It's gone from 0 to 0.75 meters. So our mass is 500 kilograms. G is 9.81 newtons per kilogram. And so we have the potential energy is 500 multiplied by 9.81 times 0.75. And that gives us an energy of 3,679 joules. Perfect. So let's move on to kinetic energy, our friend kinetic energy. Kinetic energy is the energy that an object has by virtue of its motion, how much it is moving. And the kinetic energy, capital E subscript K, is given as a half times the mass times the velocity squared. E equals a half mv squared. So again, we can have a look at an example of this. Let's say a Bugatti Veyron weighs about 1,990 kilograms and it's traveling, it's cruising a little bit at 200 mile an hour, about 50 mile an hour off its top speed. What is its kinetic energy? So here's our Bugatti Veyron. Here is the equation for kinetic energy. EK equals a half mv squared. So work it out, and this is what we get. By the way, you need to remember that I've said 200 mile an hour. We need to convert that back into meters per second. 200 miles an hour in meters per second is roughly 89.41 meters per second. So we plug these numbers straight into the equation. E equals a half mv squared. A half times 1,990 kilograms multiplied by 89.41 meters per second. And this gives the energy as a whopping 88,963 joules. That's nearly 89 kilojoules. This thing is a beast. Right, now this is all well and good. We've looked at potential energy and we've looked at kinetic energy. Now you know, having done GCSEs before, that you are normally going to be shown some sort of roller coaster where it's going to be converted from potential energy to kinetic energy and back to potential energy. But at A level, they like to use all sorts of things, and they'll throw in some suvat and projectile motion as well. They'll talk about the potential energy of a tennis ball as it's walloped, and then you have to work out its kinetic energy at certain points. And also we've looked at suvat equations where it will be after a specific amount of time. This is the difference between GCSE and A level. We like to combine the questions so that you constantly trying to figure out what's going on. I say we, I actually mean the exam board. The GCSEs, normally you get, oh look, I can do this question, it's about this. The A level questions, nuh-uh. Oh look, I can do this, it's about, oh, this, and this, and this. Huh. Okay, so let's have a look at combinations of these things, and let's just derive a couple of equations that can help us out. Knowing how to derive these equations will help you in your exams. All right, so if we have a simple combination, because remember that the greatest, most fundamental law of the universe tells us that energy cannot be created, nor can it be destroyed. And this means that the kinetic energy and the potential energy at the start and the end are always the same. The total energy is the same. This is assuming that no energy is lost to the surroundings. And really, on a proper practical level, actually, the energy that you do lose to the surroundings is minimal, as long as we're not talking about any impacts. If you're dropping something, the kinetic energy that you gain at the bottom before it loses energy through sound is pretty much the same as the potential energy it had when you dropped it. The air resistance and the friction as it falls to the ground and the heating effect is really, really minimal. So unless you've got completely immediate, immaculate, precise measurements, it's not going to make much of a difference to you. So we're going to assume most of the time that we have complete conservation of energy, and that total energy at the beginning is exactly the same as total energy at the end. Now at GCSE this was important because you had normally a roller coaster right at the top, and you knew its potential energy, so therefore you could work out its kinetic energy at different points, and so on and so on. You're not going to always have that information here. Okay, so the energy at the start of a scenario is the same as it is at the end. I've just said this, and we're going to assume that no energy is lost to the surroundings, as I've said. Now, this means that the potential energy and the kinetic energy are equal, most of the time. So we can say that the potential energy is equal to the kinetic energy. What does that mean? It means mgh is equal to a half mv squared. And remember all the assumptions that go before this. We have to be at the surface of the Earth, and we have to be assuming that nothing's lost to the surroundings. So we can actually get rid of the mass. If you notice, you can divide mass from both sides. Mass is irrelevant when it comes to energy. And so this proves mathematically that Galileo was correct. If you drop two cannonballs of different masses from the top of the Leaning Tower of Pisa, they should hit the floor at the same time, assuming nothing is lost. Now, obviously, we have air resistance on the Earth, and this means it doesn't work. When you drop two cannonballs of different material, one will hit the ground before the other because of air resistance. However, if you take these objects to the moon, so for example, I think it was Michael Collins who took the hammer and the feather to the moon and then dropped them on the surface of the moon, they both hit the ground at the same time. There's no air resistance and mass was irrelevant. So this means that GH is equal to a half V squared. So that's brilliant. We can now start to rearrange this and use it for a bunch of different scenarios. So let's have a look. The first one, rearranging for V. They'll always ask you to do this because it involves a square root. And the exam board at A-level are mean. I'm sorry, Mr. Exam Boards. Don't see me. So the square root of 2 times the acceleration due to gravity multiplied by the change in height will give you the velocity. This means that at any given height, you will know how far you've dropped something, you'll know the acceleration due to gravity, you know what 2 is, so you're always able to calculate the velocity at any single point on its journey. And then you can calculate the change in height. These are just simple rearrangements of the equations. So the change in height is given as v squared divided by 2g. And again, this is perfect. That means if you know the velocity of something that's fallen, you will always know, given the acceleration due to gravity of that place, exactly where it started from. So you can do this on the moon because you know g on the moon. You could do this on Earth. You could do this anywhere. Let's have a look at an example. Let's say, we'll take the example from the book, that a coin is dropped from the top of Nelson's column. Nelson's column is about 52 meters tall. Unfortunately, our Lego construction worker is at the bottom, and this really over large coin is about to fall on his head. The great thing about this is even though I've made the coin overly large, it doesn't matter about its mass. But we'll see what velocity it's actually going to hit him at. So off it goes. Splat. That's very unfortunate. Apologies to you, Mr. Construction Worker. So how fast did that hit him? Is he actually going to survive? Well, let's have a look. We use this equation now. V equals the square root of 2gh. So we know that h is 52 meters, g is 9.81, and 2 is 2. So v is 2 times 9.81 multiplied by 52. And that gives v equal to the square root of 1020, which is about 31.9 meters per second. 31.9 meters per second is very fast indeed. Unfortunately, I don't think Mr. Construction Worker, hard hat or not, is going to survive this. Alright, so for those of you in my Year 12 class, what I would like you to do now is please do questions 1 to 5 on page 44 of the textbook. This is a reference to the textbook for those of you who haven't got one. It's EDEXCEL AS A-Level Physics by Miles Hudson, and that's by Pearson Publishing Press, 2015. You can purchase this from the Amazon link down below. If you do that, I get a very, very small kickback, but it does help the channel quite considerably. All right, let's move on from energy and go to doing work. What is doing work? And students often ask me that for a bunch of various reasons. Students are terrible at knowing what work is. But that beside the point, work is given as a transfer of energy. The work done is the amount of energy transferred. And because it's an amount of energy, it's measured in joules, just like energy. So, if we have a mechanical force doing mechanical work, we can multiply the force by the distance moved in the direction of that force. So if I'm applying a force here and this thing's weirdly moving that way, then we cannot calculate the work done in this direction. But that doesn't make sense. So we give that as delta W equals F, the force, times the change in displacement, delta S. Nice and simple. Let's have a look at our construction worker again right at the beginning. Before he got hit by the oversized coin, he's lifting the block of 500 kilograms. Could you have a go at convincing yourself that the work done is exactly the same as the potential energy gained in that example? All right, so now our construction worker is on a slide. He's got hit in the head, he's managed to survive, and now he's taking the small pleasures in life and he's going down slides. Now, work is still being done. There is a force. Gravity is pulling him down towards the Earth, the center of the Earth. However, there's no direct route straight down towards the center of the Earth. There is a slope. So how do we solve this problem? Well, just like all forces in A-level physics, we calculate using trigonometry the directions of the force. So our first force is this, it's the weight, which I've just labelled as mg to save some time, mass times gravity. Now, we don't need the contact force here, but what we do need is we need to understand where the friction is going. And let's assume for a moment that this construction worker is going to slide down the slide at a constant velocity. If he's going at a constant velocity, this means that the friction is exactly the same as the force pulling him down the slide, this one here. And there is an angle between the force going down the slide and his weight going towards the center of the Earth, and that's given by the angle theta. Now this force is a component of the weight. If you do the parallelogram rule, you can calculate this force using trigonometry. And so we do. We use, there he goes, we use friction is equal to mg cos theta, because mg cos theta is the component of weight in that direction. And we know that that's exactly the same size as the friction. So we can calculate the work done now because we know his displacement. We would know his displacement, that's mg cos theta times the displacement gives you the work. So we end up with work as displacement times mg cos theta. So we've got no particular numbers here for an example, but this is what we do. We simply resolve the components just like we normally would in any forces equation and crack on with that. Okay, let's move on into power. Power is the rate of transfer of energy. So if you've got energy and it's being transferred very, very quickly, then you have an incredibly high power. If you're transferring the same amount of energy just really slowly, then you've got a really low level of power. Now that is going to play havoc with the sync with the audio. Let's see how long it takes me to edit that. Okay, so physics joke. What is the unit of power? Yes, that's right. What is the unit of power? Ha. Endless amounts of fun. So, moving on. We can also obviously give the units of power as joules per second because it's an energy rate of change of energy. But the watt is the SI unit. So let's have a look at the equation. The power is given as the energy transferred divided by time. P equals E over T. Simple. Why are you telling me this, Mr. Redaway? We did this at GCSE. I know! But let's have a look. I've just told you that energy transferred is work done. Now I've got another equation for power. Power is equal to the work done divided by time. So P equals the change in work divided by time. Ah, amazing. And now I can think about this and I know that work done is force times displacement. So now power is force times displacement divided by time. F delta S over T. Superb. So let's have a very quick look then at efficiency. And efficiency is not an aquatic term. Pause for laughter. Or to watch the tumbleweeds and listen to the crickets. Anywho, what is efficiency? Efficiency is simply the amount of energy actually transferred to something useful. And I know that that's not often that we see that in school because there's so much energy wasted. It hurts. But no, efficiency is the amount of energy that's put into something useful. So we can measure that with a simple ratio. The amount of useful energy that comes out, the amount of useful work done, divided by the total amount of energy you put in, is equal to the efficiency. Now let's take a quick look at different ways to measure efficiency. The useful energy output divided by the total energy input is exactly the same. But remember that the useful energy is power divided by time. All right, I believe this one to be wrong, so I'm going to double check it. But I think that power multiplied by time is gives you the energy, because power is the rate of energy transferred. So P equals E over T. So therefore E equals P times T. So this is incorrect. I apologize for my slide being incorrect. Or slide. But anyway, the effect is the same. You can see that time can be taken out of the equation here. So we've got efficiency is useful power divided by total power. All right, well, thank you very much for watching. I've been Mr. E, and I hope that you can subscribe and like and leave a comment down below. All these things are free to do, helps with the engagement of the channel, really helps the channel out, makes me feel happy. Check out this playlist, and it's probably over here now, but check out this playlist and this video that YouTube is suggesting. Also, feel free to subscribe to me and watch me open Pokemon as well. Right, last thing to do then is to say stay safe. I'll see you soon.